Welcome to Chapter 4. This is our last chapter of the semester, and it is all about exponential and logarithmic functions. So you may or may not have noticed that in this course so far, we have kind of almost pretended that these kinds of functions, along with trigonometric functions, don't exist. We've spent a lot of time developing skills using just polynomials or rational functions, like fractions with x up top and bottom. And in the last few weeks of the semester, we're actually going to discuss exponential and logarithmic functions. We will take some time to review each of these separately, and then, of course, we will talk about their derivatives, which is going to be the calculus stuff. So we will begin by talking about exponential functions, which in 4.1, we will spend some time reviewing what they are. In 4.2, we'll talk about a very specific kind of exponential function, the natural exponential function. And then in 4.3, we'll talk about the derivative of exponential functions. So let's make sure that we're all on the same page about what an exponential function is. Most people will throw this word around outside of math class to describe anything that just grows quickly as, oh, it's exponential growth. And this is actually not the case. Like, there's a very specific definition for what means or what constitutes exponential growth. So here is the definition of that, like in words. So what we mean when we say that a quantity or like an amount of something increases or decreases exponentially, right? That's what we're trying to just kind of intuitively define here, increasing or decreasing in particular in this way exponentially. This means that it will grow or decay. And here's the keywords: at a rate that is proportional to the current amount. So what the heck does that mean? Well, we are in calculus and we've been talking about rates of change, and so that has to do with the derivative and how fast something's changing. We'll actually talk more specifically about this in section 4.6, but the proportional to the current amount means that the way that the quantity is changing, the rate, it's kind of dependent on how much of the quantity that exists or how much that there is. Okay, so another way to think about this might be like the more there is, the more is gained. Or if you have less, then the less you lose. So some typical examples of exponential growth or decay, there are several, but the very typical ones that we see a lot are, for one, population growth. Now, population growth actually is more accurately modeled by something called a logistic growth, which we will talk about a little later on. But the idea of exponential growth, meaning that the rate of growth is proportional to the current amount, does apply to population growth, right? Because the more people that there are, the more generally they reproduce and the more that the population grows, right? The rate of change is dependent on how many people or animals or whatever are in the population that is being described. Along the same vein, like if you are looking at some kind of experiment where you are growing bacteria or something like that, then bacteria growth, or maybe hopefully not in your kitchen or something, the amount of bacteria there, if there's more of it, it actually spreads faster, right? The rate of change there's more to reproduce, so it has a higher rate of change or a larger rate of increase. Spread of disease is another good example of exponential growth. Yeah, this one is technically better modeled by what is called logistic, but we will again talk about that later. But again, the idea of this rate being proportional to the current amount, well, the more people that are sick with a disease, right, the faster that it can spread. And so that's the idea here, right? The rate of spread is related to how many people are sick. One more example of exponential growth has to do with economics, and we'll actually talk about this one in detail. Compound interest. Right, so the more money that you have in an account, the more money is gained by the interest. The compounding means that your interest that is gained gets added on to the amount in your account, and then you have more money in order to gain more interest on. Okay, so these are all actually examples of what is called exponential growth. We also have exponential decay, right, which is like the less is there, the less is lost, kind of like something's not growing but decaying, where you're losing the amount. And the most typical example of exponential decay, and I'm sure you've heard of this before, is radioactive decay, or maybe half-life or carbon dating, like things to do with that. Right, so when you have some kind of radioactive substance, we use carbon-14 to date organic materials, and we look at how much of that is left in a substance after a certain amount of time, and we can tell based on how much is remaining, how long that this substance has been around because of the half-life of this radioactive substance. Great, so we'll talk about that a little bit. We'll look at an example of that. But for now, here is what we mean when we say that something is exponential in its growth or decay. All right, now here is just a kind of hopefully fun and interesting little example for us to consider and kind of just compare exponential growth and non-exponential growth and see a little more clearly what does it look like when something grows exponentially. So these numbers might be a little outdated. Hopefully that you get a starting job that has a salary that starts at more than 30,000, but we take what we can get. So suppose you have these two different options. Option A is to have a job that starts at 38,000 a year, and every year you will get a $1,000 raise. Your other option starts lower at only 30% per year, and they tell you that you will get a 6% increase per year. And you have to decide, right? Which should you take? All that you need to do to figure out what will be best for you if you decide to keep this job after, for a certain length of time, is to just do a little bit of math. So let's compare the different situations. So option A seems a little easier to think about. So if you start at 38,000, right, your raise amount in your first year is going to be 1,000, right? So your salary the next year will be 39,000. Right, again, in year 2, you'll get another $1,000 raise, so your salary the year after that will be 40,000, right? And every year, this is just the same, $1,000, $1,000, $1,000 every single year. So if we just look at the first 8 years of this job here, after 8 years, you will have a salary of $46,000 based on your raises. Okay, so that $1,000 is kind of shown here, right, in this table, where every year here we add $1,000 to the salary, right? That's what's happening. This kind of growth is linear, right? We have like a constant rate of change every single year. Whenever that happens, the only function that fits that is a linear equation or a linear model. Okay, when you are adding the same thing over and over again. And that 1,000 actually represents the slope. Like we could get a formula for this. We could say that your salary is equal to the base amount, 38,000. That's actually our y-intercept. And then we add $1,000 times the year. So maybe we'll call that t. Right, that's a linear equation. Let's compare that with option B and see what happens in this case. So in option B, we will take our 30,000 and multiply that by 0.06 to get our raise amount, because that will be 0.6. Right, so our first raise amount is actually going to be more than our previous option A. So this will be 1,800. So that means that the salary after our first year, when we increase, that'll be 31,800. Okay, if we look at this new salary now, then we're going to get a 6% increase from that in the next year. So if we multiply that by 0.06 to get our 6%, then that comes out to be 1,908. So we're going to add that to the 31,800. And that comes out to be 33,708. Now we're still, very far behind. We haven't even started to, we're not even to the starting salary of the previous option. Let's keep going and see what our raise amounts will be each year. All right, so at the end of 8 years of sticking it out through this job, you can kind of compare our different salaries here from the linear amount. And we can see that around year 7, it takes 7 years here for us to sort of overtake the other salary. And then this will continue to increase even more rapidly than the just linear growth from option A if you stick around for a long time. Right, this growth here is not linear because we're not adding the same amount every time, right? This is changing. And this is changing based on the amount that we have, right? So this is exactly what is, described as exponential growth. And to get from, one sort of salary to the next, what we do from here to here, we're not multiplying this by 0.06, but we're multiplying this by 0.06 to get our raise, and then we're adding it to the original. So this is actually multiplying by 1.06, or that we've got 100%, and then we're adding 6%. And so this multiply by 0.106, multiply by 1.06, sorry, multiply by 1.06, right? Every single time, that's how we are getting to the next year's value. Okay, so our salary in this case is, again, exponential growth, where you have kind of a proportional relationship as opposed to just adding to get to the next one. Okay, so the formula for this, and we don't have to worry too much about this at this point, but just so you can see the difference, right? The salary is going to be our starting salary, 30,000. And then we are going to multiply this by 1.06 a certain number of times, right? That's what we're doing, like repeated multiplication here by the same value. And the number of times that we multiply by 1.06, I missed one here, that happens here too, is just the number of years. So that means that we'll have this in the exponent, t as our variable in the exponent. So this is what exponential functions look like, right? We've got our variable up here in the power, and that makes all the difference. Okay, so this isn't anything like related to your homework or website or anything, but I just wanted to maybe remind you or even illustrate to you for the first time what the difference really is between linear and exponential growth, right? It's this whole constant adding versus constant multiplying. So let's shift now to talk about what the functions look like. Like, what's the mathy definition of exponential growth? All right, so an exponential function, mathematically defined, is one that has this shape or this form or this personality, or the formula has this particular setup. Okay, so it's some number possibly times some other number raised to a variable power. Okay, so the x here, right, is of course our variable. And so in the exponential functions, we have our variable in the exponent. And again, that makes all the difference. Instead of x squared, we will have 2 to the x, right? The roles kind of switch when we have exponential versus polynomial functions. The example we just looked at, I was using t instead, but this a here, right, was our starting amount, the $30,000 salary. And the b here was the thing that we were repeatedly multiplying by for every year or for every increase in our variable. Okay, so these a and b have specific roles. This a here is the starting point or the initial value, or graphically, as we'll see, the y-intercept. Okay, and then the b here is called the base, right? It's the thing that is repeatedly being multiplied by. We do have some restrictions on the base. It needs to be positive because if you raise negative numbers to different powers, you kind of get this alternating positive, negative, and we don't want that flip-flop behavior. So the base has to be greater than 0, and the base, we say, can't be 1 because 1 to every power is just 1, and that's just a constant function. These kinds of functions are really cool because they tend to model a lot of things that you might be studying or be interested in. Like a lot of real life situations can be modeled by exponential functions, and in particular, the natural exponential function, which we will talk about in 4.2. But for now, here are some examples of exponential functions and not exponential functions. Okay, so of course, just a simple number to a power, like 2 to the x, is exponential, whereas x to the second is not exponential, right? We need that x in the exponent and not in the base. Here's another example of something that is exponential, 3 times 10 to the x. Right, we've got 3, that's our initial value, the a here, and then the base is 10, and we're raising that to the x, and that's exponential, right, as long as we have our variable in the exponent. Not exponential, here's just another example. X to the 10th would be a good example related to this, but can you even just point out like x to the x? That's not exponential. We need only a variable in the exponent, not in both the base and the exponent, so that would be a problem. It's actually a really interesting function, but we won't talk about that in this class, unless you want to come hang out and discuss it with me. Here's one more example. We could even have our base be maybe a fraction or a decimal. Doesn't have to be a whole number. So here it's 4 times 1/2 raised to the x, right? So here the a initial value is 4, and then the base here is 1/2. Okay, here's one more example of a non-exponential function, -3 to the x, right? We can't have our base be negative. It's got to be positive. So this is not an exponential function.